Alrighty, so we are on page 17, I believe. Page 17. Our last topic for this unit, up here, guys. Our last topic for this unit is y-intercepts and then looking at tables of values for trig functions. The tables of values aren't going to be anything like wildly new. It's going to be a different way that we can kind of organize some information here. And then we'll talk about y-intercepts. That idea will be, again, not brand new. We've talked about y-intercepts before. We're just going to apply that now to our trig functions. So to start, I'm going to look at some tables of values for some exponential and log functions, right? These are not trigonometric functions. So let's talk about how I would create a table of values for, we'll start with f of x. If I wanted you to fill out a table of values for f of x, what would you do? Plug in some values for x, right? And you threw out -2 to +2. Why was that the... Love it. So we get a little negative, we get 0 in there, we get some positive numbers. It's sort of a little spread of the variety of inputs that we can have. The only thing that we're not inputting would be fractions with your list, which frankly I'm okay with, because if I use a fractional exponent, remember that would be some sort of root. And is there any nice root of 2? Is there a nice square root of 2 or a cube root of 2? No. So I'm okay with that. We're picking values that give us a good sort of spread of our function, but also are manageable for us to be able to plug in for x. So I'm going to use your -2 to +2. That sounds great. And when I plug these in, let's see, we're plugging these in for x. So 3 times 2 to the -2nd. Remember, those negative exponents tell me to take the reciprocal. So we'd have 1/2 squared. So that'd be 3 times 1/4, which is 3/4. And then when I plug in 1, 3 times 2 to the -1st, which would be 3 times 1/2 to the 1st. So 3/2. 3 times 2 to the 0 power would be 3 times 1, which is 3. 3 times 2 to the 1st is just 3 times 2, which is 6. And then 3 times 2 squared would be 3 times 4, which is 12. Not too bad. We've done this before. We may have even made this exact table before. We've done tables with exponential functions before. We've also done tables with log functions before. So I want to make a table of values for the function log base 2 of x. Now there are some considerations I need to keep in mind when I'm taking a log, specifically values that are okay for the argument and values that the argument cannot have. So the argument of our log, right? In this case, it's just x. What do I know has to be true about the argument of my log? It needs to be positive, greater than 0, right? We cannot have 0 for the argument. I know that this needs to be greater than 0. And then I also may want to be a little selective with the values that I choose for x. When we looked at tables for log functions in, what was that, Unit 1 maybe, Unit 2, something like that, we rewrote these pretty frequently. This is going to be my y value, my g of x value. And remember, x is not the exponent this time. It's after I take the exponent what I have. Okay? So what kind of values might I want to select for x here? We know it can't be negative, and we know it can't be 0, because there's no power of 2 that would give me something negative. There's no power of 2 that would give me 0. Powers of 2 would be good, so throw a couple at me. 2, 4. Okay, you said 8, I think. I would also say we could use 1. Is that fair? And then we didn't use fractions for x for our exponential function. But it actually wouldn't be too terrible to use a fraction value for x here. What might be a good fraction that I could use? 1/4 would be good. I'm even going to back that off a little bit and do a half, but 1/4 would also work, right? A reciprocal power of 2. Okay, it's the same idea, but the reciprocal. So then for g of x, if x is a half, what did my exponent have to be? -1. If 2 to the something is equal to 1, what did our exponent have to be? 0. How about if it's 2? 1. If it's 4, 2. If it's 8, 3. So there was a little strategy to how we picked our x values here, right? I wanted a good picture of my function we talked about with f of x, with that exponential function, but I also wanted values that would be manageable. So even though we could use fractions for inputs in f of x, root 2 or cube root of 2 or fourth root of 2 isn't going to be something that's a nice value. And if we're talking about using a table to maybe graph eventually, I want stuff that I'm going to be able to graph relatively cleanly. For g of x, I was limited by the domain of this function, right? Our x values had to be greater than 0, but then we were also selective in what those values were. Could we have plugged in 3 for x? Could I do 2 to some power and get 3? I mean, technically, yes, but is that a value that's going to be nice that I can evaluate without a calculator, that I can plot cleanly on a graph? Not so much. So we're picking values that kind of make our lives a little bit easier here. So with that in mind, I want to talk about making a table of values for some of our trigonometric functions. So we're going to start with sine of x. Okay, let's consider the function f of x equals sine of x. Okay, we're going to make a table for this. And then we're going to determine if we've got a y-intercept in our table. If we are talking about using sine of x as our function, let's talk about what might be good values to use for x. Could I use 0? Think about our unit circle. 0 on there? Yeah, it is. I can use 0. Let me sketch my unit circle off to the side here. Sure, we could do 0. Could I take the sine of 1? Could I versus do I want to? Could I? Sure. Do I want to? No. Could I do the sine of 2? Could I? Yes. Do I want to? No. What are some values I might like to do for sine? What are some like places that it's easy to evaluate sine? Pi, right? What else? Pi would be over here, right? Pi over 2. What are some other values that we've talked about? 3 pi over 2. Give me some others. 2 pi, right? Negative pi, if I wanted to, right? We had some in here too, right? Pi over 3, pi over 4, pi over 6. Okay. So while I'm making my table of values, like, why for sine would I choose to evaluate sine of 5, right? I have no idea what sine of 5 is. I can approximate that it's going to be a little less than 2 pi, right? Because 2 pi would be a little more than 6. So if I were to plug in sine of 5, I mean, I could sort of estimate about, if I sketched it out, where that may fall and get maybe a close guess. But why, if I have this whole list of values that we've been working with that we know? So let's do some first quadrant values. Let's do 0. We'll do pi over 6, pi over 4, pi over 3, and pi over 2. We'll stick in that first quadrant for this first one. Okay. Assign the x or the y coordinate for that point on the unit circle. It's the y coordinate. Okay. Sine is the y coordinate. So at my point on the unit circle right here. This would be the point 1, 0. That means my sine value at 0 would be 0. Okay. For pi over 6, I want you to notice I'm not getting out my unit circle. Okay. I'm going to reason through as we're practicing these. I'm going to reason through what these values should be based on our special right triangles, because that is a skill I want you to practice. I want you to work on. Okay. I'm not pulling out my unit circle here. Okay. I don't have a unit circle in sight. Okay. For pi over 6, I know that that's in the first quadrant. It's not a very big angle. It's my 30-60 special right triangle, okay, where my little reference angle is the smallest angle, okay, is about 30 degrees. So I know my short side would be a half. My long side is √3/2. If I am talking about the coordinates of this point, it would be the x amount, comma, the y amount. So what would be sine of pi over 6? 1/2. Pi over 4, in my opinion, is the easiest of these sort of in between of these quadrant angles, because the x and the y coordinates are the same, right? Pi over 4 is the one that splits that quadrant in half. It's a 45-degree angle. The special right triangle legs are going to be the same. They are both √2/2. So this point is √2/2, comma, √2/2. So what's the y coordinate there? What's the sine value? √2/2. For pi over 3, that's my other 30-60-90 triangle. But instead of being the one that's got the sort of long side along the axis, it's the one that stands up taller. So it's the short side along the x-axis, which means that our point now would be 1/2, comma, √3/2. So what is sine of pi over 3? √3/2. And then finally, pi over 2. Pi over 2 would be up here. It would be the point 0, 1. So what is the sine of pi over 2? 1. Table of values for sine. What's the y-intercept? 0, right? Y-intercept happens when x is 0. So there's my y-intercept. We're going to make a couple more tables here, and then we're going to talk about y-intercepts for a few more functions. So on the next page, let's make a table of values for cosine. What kind of values might I want to pick for x here? Same deal, right? I could pick exactly the same ones I did for sine. For this one, we'll pick those maybe pi over 2 values you guys were throwing out at me. That way we get some stuff outside of the first quadrant. But yeah, I'm going to pick stuff that's like values from our unit circle, right? Some sort of part of pi, preferably the parts of pi that we talked about. So pi over 6, pi over 4, pi over 3, pi over 2, right? 3 pi over 2, 5 pi over 6, stuff like that. Stuff that we're familiar with would be good problems, good values, I should say. So we'll do the pi over 2s. So 0, pi over 2, pi, 3 pi over 2, 2 pi. Mix it up a little bit. So at 0, that would be here. This is the point 1, 0. So what is cosine of 0? 1, right? Sine of 0 is 0 because it's the y coordinate. Cosine of 0 would be 1 because it's the x coordinate. And then pi over 2 would be here. This is the point 0, 1. So what's cosine of pi over 2? 0, the x coordinate. And then pi is over here. This would be the point -1, 0. Now that we're out of that first quadrant. So what is cosine of pi? -1, it's the x coordinate. And then 3 pi over 2 down here, that would be 0, -1. What's cosine of 3 pi over 2? 0. And then 2 pi, we're back here. Remember 0 and 2 pi are at the same spot. So what's cosine of 2 pi? 1, same as cosine of 0. And our y-intercept for cosine would be 1. Last table we're going to make today, let's make a table of values for tangent. Tangent, remember, is the ratio of sine to cosine. So tangent is sine over cosine. So we're going to be looking at the y value over the x value. And we'll do first quadrant again. We'll do 0, pi over 6, pi over 4, pi over 3, and pi over 2. So for 0, right, that's here. We're looking at the point 1, 0. That would be sine over cosine. So that would be 0 over 1. The tangent of 0 is 0. Pi over 6. Is that triangle, that special right triangle. Okay. So the point that we're looking at would be √3 over 2, 1/2. Since tangent is sine over cosine, I've got to divide out these values. So that would be 1/2 over √3 over 2. Since we're dividing fractions, we'll multiply by the reciprocal of our divisor. When I do that, my 2's reduce, and we get 1 over the square root of 3. And then do you remember last week we talked about rationalizing our denominators, right? I don't want to leave an irrational number like the square root of 3 in the denominator. You really only care about this when we talk about trig values because the standard is that those points are already given with rationalized denominators. So we're going to go ahead and rationalize our denominator by multiplying on top and bottom by the square root of 3. So that would give me √3 on top. And then remember on the bottom here, this would be the square root of 3 squared, since it's a thing times itself. And when I do that, we're just left with 3. So tangent of pi over 6 would be √3 over 3. Pi over 4 was the √2 over 2, comma √2 over 2. It's all the √2's and 2's. Since both values, both the x and the y, are √2 over 2, I know that this is √2 over 2 divided by √2 over 2. So that would be √2 over 2 times 2 over √2 when we multiply by the reciprocal. So the √2's I can reduce, the 2's I can reduce, and we're down to 1. Tangent of pi over 4 would just be 1. For pi over 3, we have our 30, 60, 90 triangle, but this time standing on the short edge instead of the long edge. So that point would be, the x value is going to be 1/2 this time. and the y value would be root 3 over 2. When I look at that sine to cosine ratio, it's root 3 over 2 divided by a half. So we'll multiply by the reciprocal. And we end up with just root 3. And then finally, tangent of pi over 2. So pi over 2, we're back on an axis here. We're on the y-axis this time. This would be the point 0, 1. So sine over cosine would be 1 over 0. So what will I say for tangent of pi over 2? We're undefined. And my y-intercept is 0. The tables for today were really just practice of values that we've already found. We've already evaluated trig functions at all of these places, okay? Most, if not all of these values, you have found individually because I've asked you to tell me the sine of pi over 2 or the tangent of pi over 3 or the cosine of 3 pi over 2, okay? Most of this work we have done already, but we did it sort of separated out as individual problems. It's the same idea, just we're looking at a bunch of tangent values together now, or a bunch of sine values together now, okay? But same thing that we've been working on. Last thing I want to talk about. So we found y-intercepts for sine, cosine, and tangent. The y-intercept for sine, just do a little summary down here. My y-intercepts for sine of x, that y-intercept was 0. For cosine of x, that y-intercept was 1. And for tangent, that y-intercept was 0. We could find y-intercepts for all of those. Okay. I want to take a look at, without graphing, if our remaining trig functions will have y-intercepts or not. When we talked about y-intercepts the first time this year, we talked about how some functions don't have them. If it's a square root function that's been shifted to the right, it's not going to have a y-intercept. Some rational functions don't have y-intercepts if they're undefined when x is 0. We talked about log function, right? Have to be that argument has to be greater than 0, right? For that warm-up problem that we did. This guy would not have a y-intercept because x has to be greater than 0. So we're not going to have a place where we touch the y-axis. We're going to have an asymptote there. We're undefined there. So I want to talk about, for our remaining trig functions, will I have a y-intercept? Okay. So for cosecant, remember, is the reciprocal of sine. So this would be 1 over sine. That means its y-intercept would also be the reciprocal of sine's y-intercept. Well, if sine's y-intercept is 0, this would be the reciprocal of 0. Will I have a y-intercept for cosecant? No, we're going to be undefined there. What about for secant? Would you expect a y-intercept for secant? Yes. What would it be? 1, right? Secant is 1 over cosine. So its y-intercept would be 1 over 1, which is just 1. How about cotangent? Cotangent is, you could think of it as the reciprocal of tangent. It is also, since it's the reciprocal of tangent, cosine over sine. So either you are thinking about it as 1 over 0, or you are thinking about it as 1 over 0. And either way, you get no y-intercept. We're undefined at that spot. Questions for me for today? Okay, so the types of skills I want you to take out of today, the things that I want you to be able to do, let's say on a unit test. Evaluate our trig function, okay? which we have already done. So this was more of a review than it was something new, right? Creating our tables was just the same evaluating that we've done before. And then I need you to remember, right? One of the things that you have to be able to do with our trig functions is remember how they're related to one another. So sine is, or tangent, I should say, is sine over cosine. Sine is the y coordinate. Cosine is the x coordinate. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. So if I know a sine value, the reciprocal would be my cosecant value, okay? All those relationships that we've practiced so far, that we've learned already, we are just practicing again in a little bit different context here, okay?